I'm going to go over the Edexcel syllabus for paper 2 and explain what it means to help you pass your exam. Here's SP8, energy, forces doing work. You're supposed to be able to describe the changes involved in the way energy is stored when systems change. So what that means, when a system changes, that could be a car braking, which would be kinetic energy stored in the car getting turned into heat energy stored in the brakes. It could be a light bulb, where there'll be electrical energy getting turned into light and heat energy. Draw and interpret diagrams to represent energy transfers. So an energy transfer diagram, for example, for a bulb would be electrical energy going in and it's getting converted into light, useful energy, and heat, which is wasted energy. Explain that where there are energy transfers in a closed system, there is no net change to the total energy in that system. What that basically means is what goes in must come out. So it's the law of conservation of energy. For example, if 200 joules of electrical energy goes in, 200 joules needs to come out. Now, not all of the energy that comes out will be useful. There's only 80 joules here that's actually useful. 120 joules is being wasted. But it's still there. 200 went in and 200 came out. You just can't use this wasted energy for any further useful energy transfers. Identify the different ways that the energy of a system can be changed through work done by forces, which basically means mechanical work, and that's when a force moves an object through a distance. Using this equation, work done equals force times by distance. Electrical equipment, so electrical work, for example, could be charges moving due to a potential difference or voltage. And heating, well, that would be something like heat energy transferring from one place or object to another due to a temperature difference, which can be caused either electrically, but from current, or by chemical reaction, for example, burning a fuel. Describe how to measure the work done by a force and understand that energy transferred in joules is equal to work done. There we go. Energy transferred is equal to work done. Now remember, work done is force times by distance if you're talking about it in a mechanical sense. In other words, when you're moving things. Recall and use the equation work done equals force times by distance. So there it is there, W equals F times by D. But you could also see it as E equals F times by D, because remember, work done equals energy transferred. So it's just a case of you putting the numbers in. Describe and calculate the changes in energy involved when a system is changed by work done by forces. So in other words, it's just energy transferred equals force times by distance. So they'll just give you the numbers, you've just got to pop them into your calculator. Recall and use the equation to calculate the change in gravitational potential energy. So again, it's just this equation, and you've just got to pop the numbers in. So the change in gravitational potential energy equals mass times by gravity times by change in height. Recall and use the equation to calculate the amount of energy associated with a moving object. In other words, you've got to be able to calculate kinetic energy using this equation. Kinetic energy equals a half times by the mass times by the velocity squared. Make sure you square the velocity first before you do anything else. Explain using examples how in all system changes energy is dissipated so that it is stored in less useful ways. In other words, you always lose energy as heat and sound, and it goes to the surroundings. And that's usually because of friction. Explain that mechanical processes become wasteful when they cause a rise in temperature, so dissipating energy in heating the surroundings. Well, that's what I've just said there. Mechanical processes, in other words, it's friction. When objects move and rub, it causes heat and sound, which dissipates to the surroundings. try to memorise that statement there. It could be worth up to 3 marks. Define power as the rate at which energy is transferred and use examples to explain this definition. For example, that ties straight in with this equation. The power equals energy transferred over time. Power is measured in watts and energy is measured in joules and time is measured in seconds. So 1 watt is equal to 1 joule per second. And there we go there. Recall that 1 watt is equal to 1 joule per second. And recall and use the equation for efficiency. So efficiency equals useful energy transferred by the device divided by the total energy supplied to the device. For example, a bulb. If we put 200 joules of electrical energy in and 80 joules gets turned into useful light and we've wasted 120 joules, to get the efficiency you do the useful energy that came out divided by the total energy that you had to put in. So in other words, 80 joules of light energy came out, we had to put 200 joules in, 80 over 200 comes out as 0.4. Now if the examiner wanted you to express it as a percentage, multiply that by 100 and it comes out as 40% in this case. SP9, forces and their effects. 9.1. Describe with examples how objects can interact at distance without contact, linking these to the gravitational, electrostatic and magnetic fields involved. So what you see is that the fields interact, so that's either the gravitational field, the electrostatic field or the magnetic field. This causes attraction or repulsion and the object moves toward or away from each other. So that would get you up to 3 marks. Electrostatic forces are basically like positive charges and negative charges. So if you've got 2 positive charges, they'll repel. If you've got opposites, so positive and negative, they'll attract. And if you've got, once again, 2 like charges, but this time they are both negative, they are going to repel. Magnetic fields. So just like the electrostatic fields, magnetic fields, if you've got a north and a south, opposites attract. If you've got like poles, north and north, they'll repel. And also if you've got 2 south poles, they're like poles, so they'll also repel. And gravitational field, well, obviously the thing is with gravity is they can only attract. Describe with examples how objects can interact by contact, including normal contact force and friction. So as well as having a non-contact force, we can obviously have a contact force. So normal contact force is the force pushing upwards as a reaction to perhaps weight pushing downwards, which ties in with Newton's third law. For every action there's an equal and opposite reaction. Other contact forces could be friction, which is a force that opposes motion. So this force over here is trying to make the object move that way, and friction is trying to stop it. Producing pairs of forces which can be represented as vectors. So remember, a vector is something that's got size and direction. So these arrows have got a size and they've got a direction. 9.2. Explain the difference between vector and scalar quantities using examples. So a vector has size and direction, whereas a scalar has size only. Some examples of scalars are speed, mass, energy, distance. Some examples of vectors are velocity, acceleration, weight and displacement. The most common ones is if you give speed a direction, it becomes velocity, and if you give distance a direction, it becomes displacement. 9.3. Higher only. Use vector diagrams to illustrate resolution of forces, a net force, and equilibrium situations using scale drawings only. So in other words, if you've got one vector with the size and direction, let's call it A, and then another vector B. If you add A to B, you'll end up with C, which is the resultant. Now let's see how that gets applied with scale drawings. So just say you've got this object here, and the examiner tells you there's 10 newtons of force up and there's 40 newtons of force down. With a scale of 1 centimetre for 10 newtons, what you need to do is draw a parallelogram of forces, or we use the tip-to-tail addition of vectors. So in other words, if you picked this vector up and take and add that tail to this tip, so pick that up and pop it there, draw it there, and also if you picked this vector up and draw it onto the end of this vector, what you'll end up with is this vector here, which is the resultant. Now all you need to do is measure it with a ruler, and every 1 centimetre would be 10 newtons for this particular scale. Now sometimes they can give you the resultant and they ask you to break it down into its components. So the vertical component would be this one, and the horizontal component would be this one. Again, they'll give you a scale and you just measure with your ruler. So if you were to measure this with this scale, it comes out as 173 kilonewtons, and if you were to measure the length of this with that scale, it comes out as 100 kilonewtons. 9.4, again higher. Draw and use free body force diagrams. So you've got 2 newtons of force getting represented that way, 5 newtons of force getting represented that way, and you'll end up with a resultant of 3 newtons that way. So obviously if it's like tug of war, this 5 newton team has won by how much? By 3 newtons. Again higher. Explain examples of the forces acting on an isolated solid object or a system where several forces lead to a resultant force. So that's what I've just said there. On an object, and the special case of balanced forces when the resultant force is 0. So in other words, if I follow this down here, this time you've got 5 newtons to the left, 5 newtons to the right. That's going to cancel out to give 0 newtons of a resultant. So in other words, the object will remain stationary if it's already stationary, or it'll move at a steady speed. And that ties in quite nicely with Newton's first law, because it is Newton's first law. If you had a resultant force, that's Newton's second law, because that's going to cause acceleration. If you know the size of the force acting on the mass, you'll be able to work out what the acceleration would be. And finally 9.10, back to foundation and higher. Explain ways of reducing unwanted energy transfer through lubrication. In other words, applying oil. So if you apply oil to moving objects like a gearbox or a bike chain, it will reduce friction, which reduces heat and sound that gets wasted to the surroundings. Okay, if it's worth 3 marks, that's what you see. The oil reduces friction, which causes heat and sound to be lost to the surroundings. SP10, Electricity and Circuits. 10.1. Describe the structure of the atom limited to the position, mass and charge of protons, neutrons and electrons. In other words, you've got to know where each of these particles are in the atom, what their mass is and what their charge is. So the proton is found in the nucleus. It's got a mass of 1 and a charge of +1. The neutron is also found in the nucleus. It's got a mass of 1 and a charge of 0. Neutron is neutral. Proton was positive. And the electron is found in shells that orbit the nucleus. Its mass is approximately 2,000 times lighter than the proton and the neutron. It's 1/1835 if you want to be precise. And the charge is -1. 10.2. Draw and use electric circuit diagrams representing them with the conventions of positive and negative terminals and the symbols that represent all of these things over here. So the cell, the positive side of the cell is the large side. What I tell my students is if you add something, it gets bigger. So the big side is the positive side and the smaller side is the negative side. And that goes for the battery as well. So we're only interested in the outermost part of the battery there and then the outermost part of the battery there. So that was big, so that's the positive side of the battery, and that was small, so that's the negative side. Closed switch, Harry Potter's glasses. I've got a nice video that goes over all of these. Voltmeter is a circle with a V, it measures voltage. Ammeter is a circle with an A, it measures current. Open switch is Harry Potter's broken glasses. Resistor is just a box. Variable resistor is just a box with an arrow through. I like to think of the arrow there as like an upside down V, V for variable. A lamp can be represented either as an X-Man badge or as an omega sign inside the circle. The motor is a circle with an M. Diode is D, I, O, first three letters of diode. A thermistor is a resistor with a thermometer through it, or it looks like a golf club. An LDR is a light dependent resistor, so that's a resistor in a big circle to keep it dry because it goes on top of lampposts. And here's the sun shining down on it. And an LED is a light emitting diode, so it's a diode D-I-O that gives off light. 10.3. Describe the differences between series and parallel circuits. A series circuit has only one loop. A parallel circuit has more than one loop. Recall that a voltmeter is connected in parallel with a component to measure the potential difference of voltage in volts across it. So there you go, we're trying to measure the voltage of that bulb. So you put your voltmeter in parallel across the bulb. 10.5. Explain that potential difference. Voltage is the energy transferred per unit charge passed, and hence that the volt is a joule per coulomb. So in other words, it's basically this equation here. Voltage equals energy over charge, which is down here. So, but rearranged, E equals Q times by V. So energy, EastEnders, is the Queen Vic. Energy, charge, voltage. You're very often asked for an alternative unit for a volt, so make sure you memorize 1 volt is the same as 1 joule per coulomb. 1 volt is 1 joule per coulomb. Recall that an ammeter is connected in series with a component to measure the current in amps. So here we go, there's the ammeter in series, so one thing after another. Doesn't matter if the ammeter is before or after the other component. 10.8. Explain that an electric current as the rate of flow of charge, and the current in metals is a flow of electrons. So current is how much charge you've got divided by time. In other words, it's the rate of flow of charge. 10.9. Recall and use the equation charge equals current times by time. The way I like to remember that is when you're charging your mobile phone, you need to put a current into your battery, so that's why you plug it into the wall and you leave it plugged in for a certain amount of time. The more time you leave it plugged in for, and as long as there's a big current going in, then your mobile phone will get charged. And 10.10, describe that when a closed circuit includes a source of potential difference, there will be a current in the circuit. So a closed circuit just means a complete loop, and what we're basically saying is it's at the potential difference or voltage that creates or causes the current. So if you've got no voltage, you won't get any current. So what came first, the chicken or the egg? We're not sure, but what comes first, the voltage or the current? It's the voltage. 10.11. Recall that current is conserved at a junction in a circuit. That's Kirchhoff's law, which basically says current into a junction equals current out of a junction. They'll often ask you, if 4 amps goes into a junction and 2 amps comes across here, how much is coming down there? So it's obviously 2, because what goes in to a junction must come out. And same over here, 2 amps and 2 amps are joining back together and 4 amps are coming out. 10.12. Explain how changing the resistance in a circuit changes the current and how this can be achieved using a variable resistor. So we basically use resistors to control the size of the current. So if you've got a variable resistor, it means that you can adjust the resistance and that'll adjust the current. So if you make this resistance bigger, it'll make the current in the circuit smaller. Or if you make this resistance smaller, it'll make the current bigger. I like to think of a resistor as being like a brick wall. The bigger the brick wall, the harder it is to climb over it, so the slower you would go if it was like an assault course. 10.13. Recall and use the equation potential difference equals current times by resistance. This is Ohm's law. V equals I times by R. Voltage equals current times by resistance. So they'll just give you some numbers and they'll ask you to calculate something. You might have to rearrange it. 10.14. Explain why, if 2 resistors are in series, the net resistance is increased, whereas with 2 in parallel, the net resistance is decreased. So in series means one thing after another. So in series there's only one route, so the current has to go through this resistor and this resistor. So that would be the equivalent of going through a 10 ohm resistor, because there's only one path to travel down. Whereas resistors in parallel, there's 2 paths or more to travel down. So that gives the current the opportunity to take one of 2 paths. So it doesn't have to go through both resistors, it goes through one or the other. The way I like to think about it is if you've got a football stadium and there's 2 turnstiles to get into the stadium, 2 gates to get into the stadium, then you can have people going in twice as fast. And mathematically, if the current gets bigger for the same amount of voltage, then that makes the resistance get smaller. So the resistance is decreased when you've got resistors in parallel. You don't actually have to calculate the resistance in parallel anymore. That's A-level physics now. 10.15. Calculate the currents, potential differences. So remember that's just voltage and resistances in series circuits. So they might ask you to work out the current, in which case do voltage over resistance. If they ask you to work out the voltage, do the current times by the resistance. And if you've got to work out the resistance, just do voltage divided by current. And they will, of course, give you most of the numbers. And you've got to work out the final number. 10.16. Explain the design and construction of series circuits for testing and measuring. So this is your standard test circuit. You've got some kind of power source such as a battery, there's your component under the test. You need some way of getting the current. So get an ammeter in series and put a voltmeter in parallel. And then in order to get the resistance of that component, just do the voltage divided by the current. And if you've got to get multiple readings so you can create a graph or something, then you put a variable resistor in as well. So you take your current and your voltage reading, and then you adjust the variable resistor, and then take another reading. 10.17 Core Practical. Construct electrical circuits to investigate the relationship between voltage, current and resistance for a resistor and a filament lamp, and test series and parallel circuits using resistors and filament lamps. So that's using Ohm's law. And as I've just explained for 10.16, would use this circuit, and you would get the current and voltage reading for that particular device. So they're saying for a resistor and for a filament lamp. And then once you've got your current and your voltage readings, adjust the variable resistor and take your readings again, and do that a minimum of 6 times in order to get enough data to plot a graph. And here's the type of graphs that you'll end up getting. In 10.18, it's asking you about those graphs. So you've got to explain how current varies with potential difference for the following devices and how this relates to resistance. So for a filament lamp, a diode and a fixed resistor. So the IV graphs, the current voltage graph, current goes up the side, voltage goes along the bottom, and you'll notice I've done positive currents going down to 0 and then negative currents. So that's why we've got this crisscross graph here. I've got negative voltages on as well. Now this is for a bulb, or as I like to say, a spulb, because it looks like an S shape. Here is a diode, and here's the current voltage graph for a fixed resistor. Now, the flatter that the graph is, that means that resistance is increasing. So it starts off steep, so resistance is small for a bulb, and then the resistance increases. If they ask you why does it do that, you say because the bulb gets hot, and that's what increases the resistance. A diode has got a massive resistance in the reverse direction, so it doesn't matter how big the negative voltage gets, the current still remains 0. And in a forward direction, once the voltage gets to positive 0.6, then the current starts to flow. And it's a steady current, so it's a steady resistance, and it's quite a steep slope, so that means it's a smaller resistance. And for a fixed resistor, well, obviously the resistance is fixed. So you get a steady slope. Sometimes the slope can be steep, which means it is a small resistor, or sometimes the slope is flatter, which means that it's a bigger resistor. But it would still be a straight line to say that it's a fixed resistance. 10.19. Describe how the resistance of a light-dependent resistor, LDR, varies with light intensity. So if we plot light intensity along the bottom, going from dark to bright, and resistance up the side, when it's dark, the resistance is big, and as it gets brighter and brighter, the resistance decreases. Make sure you also note that the resistance decreases in a non-linear way. That's what you tell the examiner for your second mark. And that's the symbol for the LDR. 10.20. Describe how the resistance of a thermistor varies with change of temperature. So that's a negative temperature coefficient thermistors only. So negative temperature coefficient basically means as one thing gets bigger, another thing gets littler. In other words, as the temperature increases and it gets hotter, the resistance decreases. 1 mark for saying that, and 1 mark for saying it decreases in a non-linear way. So it's exactly the same shape for the thermistor as it was for the LDR. Explain how the design and use of circuits can be used to explore the variation of resistance in the following devices. filament lamps, diodes, thermistors and LDRs. So basically it's similar to the core practical. We'd use that circuit there in order to get multiple readings and to plot these graphs here and these graphs here. Recall that when there is an electric current in a resistor, there is an energy transfer which heats the resistor. So basically, if you put current into a resistor, the resistor is going to get hot. That's all you need to know. Explain that electrical energy is dissipated as thermal energy in the surroundings when an electrical current does work against electrical resistance. In other words, you tell the examiner that resistors get hot when current passes through. And if it says, where does the energy go to? You say it to the surroundings for your third mark. Explain the energy transfer as a result of collisions between electrons and the ions in the lattice. So, why is it that resistors get hot when current passes through? Well, if you were to think about it in terms of particles, the little electrons that make up the current that's trying to go through the wire collide into the ions that make up the wire, like the copper ions, you know? Now, every time there's a little collision between the electrons and the ions, there's a little bit of friction, and the friction causes heat. So that's why the resistors heat up. I've got a nice little video all to do with that. If you want to watch it, I'll put a link at the top of the screen. Explain ways of reducing unwanted energy transfer through low resistance wires. In other words, if you do not want your wires to get hot, so you want less heat, you'd better use low resistance wires. Now, a low resistance wire will be a short wire and a thick wire. The shorter it is and the thicker it is, the lower the resistance. Describe the advantages and disadvantages of the heating effect of an electric current. Well, the heating effect of current is an advantage, so it's good, if you want the device to get hot. So in other words, if you've got a heater or a hairdryer, you want that thing to heat up on purpose to create heat. Obviously, it's a disadvantage in any device not designed to get hot. So if you've got current making your device get hot and it's not supposed to get hot, such as in a phone or a PC, that basically means you could damage your components. You could damage your phone, you can damage your PC. Well, that's a big disadvantage of the heating effect of an electric current. 10.27. Use the equation energy transferred equals current times by potential difference times by time. In other words, Emmerdale is on ITV. So energy is I for current times by V for volts times by T for time. Remember to convert the time into seconds if they give you it in minutes. 10.28. Describe power as the energy transferred per second, and recall that it's measured in watts. So 1 watt of power means that you use 1 joule of energy per second. Or in other words, if you've got a 100 watt light bulb, that would use 100 joules per second. 200 watt light bulb would be 200 joules per second. Recall and use the equation power is energy transferred divided by time taken. So power is the energy you've used per second, or energy you've transferred per second. Explain how the power transfer in any circuit device is related to the potential difference across it and the current in it. In other words, power, P, equals I times by V. Another equation you've got to know is P equals I squared times by R. Make sure you know how to rearrange them. Describe how in different domestic devices energy is transferred from batteries and the AC mains to the energy of motors and heating devices. So batteries providing energy to motors, well, you'd have chemical energy in the battery, then that would turn into electrical energy going through the wires, and then going to kinetic energy of the motor moving. So 1, 2, 3 marks for that possibly. What about batteries powering a heater? Well, once again, the battery is a store of chemical energy, and then it would need to go into electrical energy in the wires, and then, well, a heater gives out heat energy, so thermal or heat energy. Once again, 1, 2, 3 marks possibly. Alternating current in the mains. Well, remember, the mains electricity comes from kinetic energy in turbines. You turn the turbine, which turns the generator, etc. Now, if it is worth 3 marks, you could say that would be kinetic energy turning into electrical energy and then going into the kinetic energy of the motor. If it was only worth 2 marks, just say the mains has got electrical energy going to kinetic energy. Again, the mains, but this time powering a heater. Well, if it's worth 3, say kinetic energy in the turbine creates the electrical energy, and then that powers the heat from the heater. Explain the difference between direct and alternating voltage. So direct voltage is just a steady voltage, whereas alternating voltage goes up and down. So it would have like a peak positive voltage going forwards, and then it would go down to 0, and then it would have a peak negative or backward voltage. So alternating voltage, just basically say the voltage alternates. Describe direct current, DC, as movement of charge in one direction. So that's literally it. So the electrons move in one direction, and that comes from cells and batteries. They supply DC. So if they say, where does DC come from, you say cells and batteries. If they say, how does the electrons move, just say in one direction. Right, describe that in alternating current, AC. The movement of charge, like the electrons, changes direction. Yeah, it alternates. That's why they call it alternating current. How often does it alternate? Well, 50 times per second, which is a frequency of 50 hertz, which is the next thing you're supposed to know. The domestic supply, the AC in England, right, in the UK, has got a frequency of 50 hertz. That'll get you 1 mark. And if they say, what's the voltage of AC, you say 230. That'll get you another mark. Explain the difference in function between the live and the neutral mains wires. Okay, so basically the live wire is what brings the current in to the electrical appliance, brings the current in, and the neutral wire takes the current away from the electrical appliance. If you want to be posh about it, you can say the live wire connects the appliance to the power station, but I'll just prefer to say it brings the current in, and you can say the neutral wire is the return path to the power station, but I just like to say it takes the current away. You'll still get the marks for that. And remember, the live wire's got 230 volts in it. That's why they call it live. And then the voltage gets used at the electrical appliance. So now there's no volts left as the current goes back to the mains to get more voltage. So, by the way, so you say there's 230 volts in the live and there's 0 volts in the neutral, but the current in the live and the neutral is the same size. The current is the same size in the live and the neutral wires. Just remember, the current in a series circuit is the same everywhere. Explain the function of an earth wire and of fuses or circuit breakers in ensuring safety. So basically, if they say, what does the earth wire do, the fuse do, or a circuit breaker do, for 1 basic mark, you just say it's for safety. If If you want to know a little bit more, the earth wire, it connects the outer metal casing of the appliance to the earth. Now, plastic devices don't need an earth wire. So you only need an earth wire if you've got like a metal kettle or a metal drill or just anything electrical that's got a metal outer casing. It needs an earth wire. A fuse is basically a glass tube with a thin wire inside. Now, it'll have a certain rating, so current passes through the wire and the wire gets hot, that thin wire. If the current exceeds a certain value, the wire melts, breaks the circuit, it stops the current, and it protects the device and the user. Now, I've seen that, how does a fuse work, as a question that's worth 6 marks a few times. So make sure you understand how it works. Right, a circuit breaker. Well, it's a bit like a fuse, but it's got an electromagnet in. So once again, if the current is bigger than the rating of the circuit breaker, so you can get circuit breakers that might be 1 amp, 5 amp, 13 amps. So if it's a 13 amp circuit breaker, and let's say the current coming in is bigger, so it's like 14 amps, what happens is the electromagnet inside gets stronger, because there's a bigger current, and it breaks the circuit by attracting an iron switch, sort of pulls a piece of iron over and it disconnects the circuit. Now, if they say what's best, a fuse or a circuit breaker, it's a circuit breaker. Circuit breakers are better than a fuse because they can be reset once the fault is fixed. And they also break the circuit faster, which prevents electrical shocks. A fuse doesn't really prevent electrical shocks, not straight away, because the fuse has to get hot, so it can take a little bit of time to melt before it breaks the circuit, whereas the circuit breaker, it just sort of breaks straight away, so much better. Right, recall the potential differences between the live, neutral and earth wires. In other words, just you've got to know the voltage of the live wire is 230 volts for 1 mark. The neutral wire voltage is 0, neutral, 0. And the earth is also 0, so the earth's for safety, so that's got 0 volts. Explain the dangers of providing any connection between the live wire and earth. So that could be like you grabbing the live wire and standing on the earth. So basically you'll get a shock. So that would create a short circuit, which would be a very low resistance circuit. Now, if the resistance goes down, that causes a very large current to flow to the earth, which causes the wire to heat up, which could start a fire. So the dangers of creating a short circuit is it could cause a fire because the current gets big. You could also get an electric shock. And describe with examples the relationship between the power ratings for domestic electrical appliances and the changes in stored energy when they are in use. Right, so basically the higher the power of the device, the greater the change in stored energy. So if you've got a telly and it's only, 100 watts, then that's only going to use 100 joules of energy per second. Whereas if you've got a massive light bulb or something, 500 watts, that'll be 500 joules per second. Remember what I've said up here. However many watts it is, that tells you how many joules per second. Unit SP12, Magnetism and the motor effect. Recall that, unlike magnetic poles attract, just like that, and like magnetic poles repel. So a north repels a north, a south repels a south, and a north and a south will attract. Describe the uses of permanent and temporary magnetic materials, including cobalt, steel, iron and nickel. Well, the first thing is make sure you know that they are the 4 magnetic materials that you'll need to talk about at GCSE. And the uses, well, the uses of permanent magnets. For 1 mark, you use them in a fridge door, or for separating recycling, like steel cans from aluminium cans. And uses of temporary magnets could be maglev trains, which is magnetic levitation trains, and electromagnetic cranes found in junkyards and places like that, where they've got to move metal from one place to another, and they use temporary magnets. What they mean by that is electromagnets, so they can turn them on and off. Explain the difference between permanent and induced magnets. So a permanent magnet is always magnetic. Well, that's easy, isn't it? It's always got a magnetic field around it. But an induced magnet, they are only magnetic when in another magnet's magnetic field. So if you just had a piece of iron, it wouldn't have its own magnetic field. But if you put that piece of iron next to a magnet, it'll gain its own magnetic field from the permanent magnet. So the permanent magnet goes north-south. The induced magnet would also be north-south. So make sure you do the north next to the south. I've got videos on my YouTube channel in all these different playlists. If ever you need any extra help, check out the full videos. Describe the shape and direction of the magnetic field around bar magnets and for a uniform field, and relate the strength of the field to the concentration of the lines. Now that's what I've just explained with the electric fields. So with a bar magnet, you've got the lines are closest where the poles are. So the magnetic field is strong here because the lines are close together, exactly the same here. And the magnetic field is weak on the outer edges over there and over here, further from the magnet. And that's because the further away from the magnet you get, the weaker the magnetic field is. We represent the strength of the magnetic field by the lines. And the magnetic fields come out of the North Pole and go into the South Pole. Describe the shape and direction of the magnetic field around a bar magnet and for a uniform field. So for a uniform field, you'd have this plate here and this plate here, which are parallel to each other. And you'd have a uniform magnetic field lines equally spaced out going from the north to the south. Notice around the edges here, it's not quite uniform, so it's just this part right in the middle between the 2 poles. Describe the use of plotting compasses to show the shape and direction of the field of a magnet and the Earth's magnetic field. So the field around a magnet, what you basically do is just put plotting compasses all over the place. You can see I've strategically placed them to show that the field comes out of the North Pole and goes into the south. So these compasses here would show the shape and direction of a magnetic field. And what you do is you just, whichever way the compass is pointing, draw a little arrow coming out of the compass on the paper next to it. Little arrows coming out like that. And then you just connect all those arrows together there, connect all these arrows together there, and just do the same coming down that way. I've got a video that shows you how to do it if you don't understand what I'm talking about. And the Earth, where the North Pole is and the South Pole is, there's exactly the same field coming out of the Earth. But obviously it's not horizontal like that. The poles would be vertical. Explain how the behaviour of a magnetic compass is related to evidence that the core of the Earth must be magnetic. Well, basically, a compass points to Earth's North Pole. That'll get you 2 marks. Describe how to show that a current can create a magnetic effect around a long straight conductor, describing the shape of the magnetic field produced and relating the direction of the magnetic field to the direction of the current. So you want to use the right hand grip rule for a straight wire. So point your thumb up, point your fingers round like that. Your thumb shows which direction the current's going, as it's going through the wire. In this case, the current's going upwards. And the fingers would show which way the field goes. Now, the magnetic field direction is from north to south, same as usual. Knuckles is north, and fingertips is south. So if you pointed your thumb up, your fingers would come around in a circle like that. If you were looking down on it, it would be anti-clockwise. And the current is conventional current, which is from positive to negative. Recall that the strength of the field depends on the size of the current and the distance from the long straight conductor. Yep. If you increase the size of the current, that'll make it a stronger magnetic field. And if you are closer to the wire, you'll have a stronger magnetic field. So a strong magnetic field next to the wire and a weak magnetic field as you move further away from the wire. You can see these lines here are close together, but these lines further apart are further apart. We always use the lines to represent the strength of magnetic and electric fields. Explain how inside a solenoid, so that's an example of an electromagnet, which is basically just a coil of wire. That's what a solenoid is. The fields from individual coils add together to form a very strong, almost uniform field along the centre of the coil. That's that there. And they would cancel out to give a weaker field outside of the coil. All right. So the magnetic field from here interferes with the magnetic field out there. And you end up with a weaker field out here and a weaker field out there. And nice and strong in the middle. And you'll notice, yes, it's nearly uniform because these yellow lines that I've drawn for the magnetic field are nearly parallel to each other. Notice that the right hand grip rule for the solenoid is different to the right hand grip rule for a straight wire. The thumb this time doesn't represent the current, it represents the direction of the magnetic field, and the fingers this time represent the current, where the current's going. So the current's going from the front of the screen to the back of the screen, front of the screen to the back of the screen. Well, you can see these fingers are coming from the front down to the back. But it's only worth 1 mark, so you'll not need to know that. Recall that a current carrying conductor placed near a magnet experiences a force and that an equal and opposite force acts on the magnet. Well, that would be the same as placing 2 magnets together. So if you placed a magnet inside this magnetic field, it's going to repel or attract. Explain that magnetic forces are due to interactions between magnetic fields. Yeah, that's just a statement. Recall and use Fleming's left-hand rule to represent the relative directions of the force, the current, and the magnetic field for cases where they are mutually perpendicular, which means all at 90 degrees. So Fleming's left-hand rule is this here. Your thumb represents the movement, first finger represents the magnetic field, second finger represents the current. I've got a nice video on that if you want to know more. Use the equation F equals Bill. So that's the force on a conductor at right angles will equal the magnetic flux density times by the current times by the length. So if it is on your exam, they'll just give you the equation and the numbers and just pop them in. SP13 Electromagnetic Induction. Higher only. Recall the factors that affect the size and direction of an induced potential difference. In other words, the size and direction of the voltage, and describe how the magnetic field produced opposes the original charge. That should say original change. So that's just something that'll get you 1 mark in an exam. Just say the magnetic field produced opposes the original change. Right, so the size and direction. The size of the voltage and the current will get bigger if you have faster movement of the magnet into a coil of wire, or if you use a stronger magnet into a coil of wire, or you have more coils on the coil of wire. So imagine that this is your coil of wire. To make electricity, you just basically shove a magnet in to the coil of wire. There's your north and there's your south. Now if you push the magnet in, you might get a positive voltage and a positive current. And if you reverse the magnet, so if you pull the magnet out, you're gonna get a negative voltage and current. So the magnetic field produced is going to oppose the original change. So just say pushing it in makes it positive. That would mean if you pull the magnet back out, that's going to be negative voltage and current. So if you reverse the movement, it'll reverse the voltage and current. Now, instead of pushing the north in and you end up getting a positive voltage, if you reverse the magnet, so this time the north's on the left, and I push the south in, you'll actually end up with a negative voltage and current. So if the magnet gets reversed or the pole gets reversed, that'll reverse the voltage and current. Just remember the word reverse. If you reverse the movement, it's going to reverse the voltage and current. Or if you reverse the magnet, it's going to reverse the voltage and current. Again, higher only. Explain how an alternating current in one circuit can induce a current in another circuit in a transformer. So this is a transformer here. If you put voltage into the primary, it can create a voltage in the secondary. That's all it means. And if you put an alternating current in, you can get an alternating current out. Now this transformer, all transformers only work with alternating current. So I've seen them ask a trick question. If they say they put DC in, how much DC voltage will you get out? Well, you won't get any, because transformers only work with AC. Higher only again. Recall that a transformer can change the size of an alternating voltage. So 1 mark for saying that. Extra details is you've got to know there's 2 types of transformers, a step-up transformer and a step-down transformer. Whatever it says it does, that's what it does to the voltage. So if it says it's a step-up transformer, it's going to step up the voltage. If it says it's a step-down transformer, it's going to step down the voltage. In other words, step-up transformers have a small voltage in and you get a big voltage out. Whereas a step-down transformer, you put a big voltage in and it steps the voltage down, so you only get a small voltage out. Now you can recognize a step-up transformer because you end up with more turns on the secondary. Imagine you've got a little person standing there, right? To go from there up to there, they have to step up. That's what I say to my students. So that's a step-up transformer. Whereas if there was a person standing on here, those coils, they've got to step down to get onto those coils there. So this could be like 10 coils on there and 20 coils on there. You get more coils, so you've got to step up. And then this one could be like, I don't know, 30 coils on there, just going down to 10 coils on there. That's stepping down. Explain why in the national grid electrical energy is transferred at high voltages from the power station and then transferred at lower voltages in each locality. So in other words, next to someone's house or next to the factory or a hospital. For domestic uses, as it improves the efficiency by reducing heat loss in the transmission wires. Okay, so here's your national grid down here. If they ask you what is the national grid, you say it's the power station, it's a step-up transformer, then it's the pylons, and then it's a step-down transformer. So that is the national grid. And it connects the power station to the consumer. So those wires might go over farmers' fields and everything across the UK. Now, in the power station, right, you've got to remember these voltages. We create the voltage at 25 kilovolts, which is 25,000 volts. Now it steps it up, right, step up transformer, it makes it 16 times bigger. So it goes from 25 kilovolts up to 400 kilovolts. Now the reason we do that, we step up the voltage because that allows us to make the current smaller. Now why do you want the current smaller? Well, remember, current makes the wires get hot. So if we make the current smaller, the wires don't get hot. So that reduces electrical energy being wasted as heat energy, which would get dissipated to the surroundings. That just means it goes to the surroundings. So by having a smaller current, it improves the efficiency because it reduces what we call line loss, which is when electrical energy turns into heat energy. And all the lovely electrical power and electrical energy, it just gets wasted here. It goes off into the surroundings, so there'd be no electrical power or no electrical energy left for the poor old consumer. And make sure you're talking about electrical energy or electrical power, otherwise you won't get the marks if you just say electricity. Now, we turn it into lower voltages once we get to the end. So if you step it up at the start, you've got to remember to step the voltage back down at the end. You can't be putting 400,000 volts into the consumer, into their house or factory. Massive voltages would cause sparks to fly all over the place. So we step down the voltage to a safe level for the consumer at the end. And we try to do that as late as possible, so as close to the consumer as possible. Because remember, if we step down the voltage, that's going to make the current go big again. And as soon as the current goes big again, you're going to end up losing heat. You're going to get that line loss coming back. So we wait right until the last minute to step the voltage back down when we're in the locality, when we're local to where we need the power. Now remember these voltages as well. At a house, so a normal sort of person's house, the voltage is 230, and if you've got a small factory, it's 11 kilovolts, and if you've got a large factory, the voltage is 33 kilovolts. So make sure you remember those numbers there, because you might get asked. Explain where and why step up and step down transformers are used in the transmission of electricity in the national grid. Well, I've just explained it all. And finally, use the power equation for transformers with 100% efficiency. So what goes in must come out. The power equation is basically the potential difference across the primary coil times by the current in the primary coil. So that's the voltage in the primary coil times by the current in the primary coil is going to equal the voltage in the secondary coil times by the current in the secondary coil. So yeah, what goes in must come out, if we're assuming it's 100% efficient. Unit SP14, Particle Model. Use a simple kinetic theory model to explain the different states of matter. So remember, that's solids, liquids and gases, in terms of the movement and arrangement of particles. So here's your three states of matter: solid, liquid and gas. Now your particle arrangement, you say that the solid is in nice neat rows, you get fixed volume, fixed shape, and the particles are very close together. As a result, the density will be very high. And how do the particles move? Well, by vibration only, because they're bonded together. The particles in a liquid are irregular, which means they're all over the place. They've still got a fixed volume, but they don't have a fixed shape. They'll fill the shape of the container. and the particles are close together as opposed to very close in the solids. How do they move? Well, the particles move slow and randomly. Particles in a gas are irregular, so it means they're all over the place. Not a fixed volume this time. A gas will fill the volume of the room. It's not a fixed shape either, and the particles are far apart. How do the particles move? Rapid and random. Or if you don't like the word rapid, just say fast and random. Recall and use the equation. Density equals mass divided by volume. So we use a wiggly P for density, M for mass, V for volume. Core practical. Investigate the densities of solids and liquids. So if you're going to investigate the density of a regular solid, for example a cube, well, always base your explanation on the calculation. So to get the density of whatever, you need to know the mass and the volume. Tell the examiner you'll use this equation. Tell the examiner that to get the mass, you'll use a mass top pan balance. And to get the volume, because it's a regular shape, you just do the height times by the width times by the depth. So just use a ruler. In order to get the density of an irregular solid, so that means like an odd shaped solid, again, tell the examiner you're going to use density equals mass over volume. Now you can get the mass once again just by using a mass top pan balance, so it doesn't matter that it's a funny shape, you can still put it on the top and you'll get the mass. However, this time to get the volume, what you'll need to do is take a measuring cylinder, so tell the examiner that, and fill it up with water to say halfway, and then plop the shape into the water and the water will rise. Now if we say the volume at first was volume 1 and the volume after you've put the object in is volume 2, then to get the volume of the irregular shaped solid, just do volume 2 take away volume 1, and that will also get you anything up to 6 marks. Now if you're going to get the density of a liquid, well, get a measuring cylinder, put it on top of the mass top pan balance, and then press the tare button to take it back to 0. When you put your liquid into the measuring cylinder, the mass top pan balance will just tell you how much mass of liquid there is. And the beauty of this is at the same time, the measuring cylinder will also tell you the volume. So you just get the mass and the volume by using a mass top pan balance using that technique. Explain the differences in density between the different states of matter in terms of the arrangements of the atoms or molecules. So specifically to do with the density, solids, the density is very high, liquid density is high, and gas density is low. So with the exception of water and ice, most solids are more dense than their liquid variant. And as they turn into a gas, so that's another physical change, generally the particles spread out even more. Describe that when substances melt, freeze, evaporate, boil, condense or sublimate, mass is conserved. So that just means the mass that goes in equals the mass that comes out, and that these physical changes differ from some chemical changes because the material recovers its original properties if the change is reversed. So sometimes if you have a chemical change, the properties will be totally different and you can't reverse it. But if you're just changing the state of matter, that's just a physical change. And if you reverse the change, you'll get the same properties back. So if we start with solid, go into a liquid, go into a gas. A solid melts and turns into a liquid, and then it evaporates or boils and turns into a gas. If you cool the gas, it'll condense to form a liquid. Once you've got the liquid and you cool it, it'll freeze to a solid. When it's a solid, it doesn't have much energy. When it's a liquid, it's got more energy. and when it's a gas, it's got high energy. And sublimate is when you turn from a solid directly into a gas without going into the liquid state of matter. Explain how heating a system will change the energy stored within the system and raise its temperature or produce changes of state. So that's what I've just said there. The solid has got a low amount of energy, a liquid's got medium amount of energy, gas has got a high amount of energy. You know, you could be asked that in your exam, you get 1 mark for each of those things. Define the terms specific heat capacity and specific latent heat and explain the difference between them. So remember, it's only worth 1 mark. Well, specific heat capacity is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree C. Specific latent heat for 1 mark in an exam, it's the amount of energy needed to change 1 kilogram of a substance from one state to another without changing its temperature. In other words, specific latent heat is what you use if there's a change of state. Specific heat capacity is what you use as you're heating one state and it's getting close to either the melting point or the boiling point. Use the equation. Change in thermal energy Q equals the mass times by specific heat capacity times by the change in temperature. Now, you'll have to rearrange that sometimes in order to find the specific heat capacity. So if you know how much energy you're putting into a liquid or a solid, and you know the mass of the liquid or solid and how much it's changed its temperature by, then you'll be able to work out what the specific heat capacity of the solid or the liquid is. Use the equation Q equals M times by L. So that's the amount of thermal energy needed for a change of state. And that's the mass times by the specific latent heat. Explain ways of reducing unwanted energy transfer through thermal insulation. In other words, wrap up something in foam or put a lid on it if you don't want to waste thermal energy from that thing. 1 mark for each of those things. Investigate the properties of water by determining the specific heat capacity of water and obtaining a temperature time graph for melting ice. So, here's how to determine the specific heat capacity of water. You'd need to fill a container with a known mass of water. And for another mark, measure the starting temperature of the water. For your 3rd mark, use a heater connected to a joule meter to heat the water. Measure the final temperature of the water. Measure the amount of heat energy used. And then calculate the specific heat capacity by using C equals Q divided by mass times by temperature change. The temperature change will be the final temperature. Take away the temperature at the start. I've got a nice little video all to do with that. Definitely recommend you watch it. Obtaining a temperature time graph for melting ice. Right, what you do is you tell the examiner that you would heat some crushed ice. You'd record the temperature and the time. So say heated for 10 minutes, record the temperature over the 10 minutes. And then use those results to plot your temperature time graph. Now what you should find is when it's ice, it'll start to heat up and heat up. Now once it changes from ice, which is a solid, into water, which is a liquid, during the melting process, you should end up with a flat part of the graph. It's what we call a plateau. And that's because it's changing state. Now, you're still putting energy in because you're still heating it. So you say, well, where's that energy gone? Because the temperature's not going up. The energy is being used to break bonds, turning it from a solid into a liquid. Once it's fully turned into a liquid, then the temperature will continue to go up. Once it reaches a change of state again and changes from a liquid into a gas, once again you'll end up getting a flat part, which is your plateau. Now these plateaus, because there's no change in temperature, that's when you'd use this equation here. Q equals m times by L. You'll notice there's not a change of temperature involved when you're using the specific latent heat as it's changing state. As it's changing the temperature, and this section here and this section here, that's when you would use the equation for specific heat capacity, which does involve the change of temperature in the calculation. Again, if you're not sure about that, check out my video from the SP14 playlist. Explain the pressure of a gas in terms of its motion of its particles. You just need to say that the pressure of the gas is because of the motion of the particles. Pressure is caused by collision of particles. For 1 mark. Explain the effect of changing the temperature of a gas on the velocity of its particles and hence the pressure. Well, if you increase the temperature, that's going to increase the velocity of the particles and that's going to increase the pressure. And it does say for a fixed mass of gas at a constant volume. Describe the term absolute zero minus 273 degrees C in terms of the lack of movement of particles. So just make sure you know that the coldest temperature you can ever get is called absolute zero, and it's at minus 273 degrees C. And at that point, there's no movement of the particles, or it's very, very minimal. And therefore, if the velocity is zero of the particles, then there'll be no pressure either. Convert between Kelvin and Celsius scales. So if it does ask you to do this, to convert degrees Celsius into kelvins, take the degrees Celsius and add 273 to it. For example, if you've got 27 degrees C, that'll actually be 300 Kelvin. And to go from kelvins into degrees Cs, you take 273 away. So if you had 300 Kelvin, that's actually just 27 degrees C. SP15, Forces and Matter. You need to explain using springs and other elastic objects that stretching, bending or compressing an object requires more than one force. Right, if you're going to stretch an object, you need one force at one end and one force at the other end, both pulling away from each other. If you're going to bend an object, you're going to need two forces on the end pushing the same way, and then one force in the middle pushing the opposite way. To compress something, which just basically means squash, you need one force on one end pushing inwards and another force on the other end also pushing inwards. Describe the difference between elastic and inelastic distortion. So elastic distortion means returns to the original shape when the forces are removed, and inelastic distortion means does not return to the original shape when forces are removed. So it would keep the new shape. So you literally get marks for saying those things there. Recall and use the equation for linear elastic distortion. So F equals Kx. So that's force equals the spring constant times by the extension of the spring. You often rearrange it to get the spring constant. You just do the force that you've put on the spring divided by how much the spring extended by. Use the equation to calculate work done. Well, remember, work done is energy transferred. Both units are in joules. So you'll notice the equation here says energy rather than work done, but it's the same thing. So to work out how much work or energy you've transferred on a spring by stretching it, you do a half times by the spring constant times by the extension squared. Describe the difference between linear and non-linear relationships between force and extension. So as I say to my students, linear basically means the straight part of the line, and non-linear is a curve. So when you're putting a force onto a spring, it'll extend. Now at first it will extend proportionally. So the force is proportional to the extension, and that's, you can tell because it's linear, in other words a straight line. Now that's what we call the elastic distortion. So if you were to take the force off, it would go back to its original shape. However, once you go past a certain point called the elastic limit, that's the end of the elastic distortion, and it's the start of inelastic distortion. In other words, if you were to take the force back off, the spring would never go back to its original length. You'll always end up with this extra little bit of extension. Okay? So it did not return to its original shape. It's been permanently turned into a new shape. Right, and the last bit is core practical, so this is important. This could be the 6th marker. Investigate the extension and work done when applying forces to a spring. Right, so tell the examiner you'd measure the original length of the spring when there's no weight on. So get a clamp stand, right? Get a clamp on the stand and hang your spring on it. Now you'd have to put a ruler next to it and get the original length of that spring when there's nothing hanging on the end. Then you would hang 1 Newton of weight onto the spring, and obviously the spring's going to start pulling down. So use your ruler to measure that new length. Then what you do, so for your 3rd mark, measure the new length. Then for your 4th mark, calculate the extension. So tell the examiner, get your new length and take away the original length. So get that new length there. I don't know, that might be 20 centimetres, and the original length might have only been 10 centimetres. Then for your 5th mark, you say repeat steps 2 to 4 until you've got 6 results. Why 6 results? So you can spot a pattern. So hang 2 newtons on, then 3 newtons, then 4 newtons, then 5 newtons. You know what I mean? The spring will get longer and longer and longer. Then for your 6th mark, tell the examiner you're going to use K equals F over X. So just make sure you put that in just for an extra mark. And you'll be able to calculate the spring constant K. Or they might be specific and say they want you to plot a graph. So you'd have to plot a force against extension graph, just like this over here. And you can calculate the gradient. If you're going to put force up the side and extension along the bottom, that's the y-axis divided by the x-axis. You're basically doing F over X, which means you're going to get K. So the gradient will be K. So calculate the gradient once you've plotted your force extension graph. Just in case you haven't got the 6 marks already, or they're very specific and they say they want you to get the work done, make sure you put the work done equation in. Tell them that you're going to calculate the work done, so half k x squared, and then even tell them repeat for different springs and compare. Now don't just say repeat, you've got to say repeat and compare. So if we look over here, if you were to get a steep slope on your force extension graph, that means the spring's stiff. In other words, you needed a greater force to create an extension. And if you get a flatter slope, that means it's not as stiff. So in other words, less force is needed to create an extension. So look, I don't know what that extension is there, just say that extension was 10. This slope only needed a little force to create the 10, whereas this spring with a big slope needed a lot more force to get the same extension. Now I have seen this as well. You are supposed to know what would a rubber band look like, so just remember that shape. It goes up like that. If they ask you to explain it, well, remember, if it's steep, if it's steep here, that means it's stiff. So the rubber band is stiff at first, then it goes flatter, so that means it's not as stiff. and then it goes stiff again. So if you've ever pulled a rubber band, that's right. It can be a little bit stiff to get it stretching, then it goes all easy to pull, and then towards the end, if you keep stretching it, it goes quite hard to pull it. And a spring, well, that was the same as before. It's directly proportional at first, so it's linear. So directly proportional would mean it goes through the origin, 0, 0, and it's linear. So in other words, if you were to double the force, that would double the extension. Then up until the elastic limit, mind, and then you're going to get your permanent extension, your inelastic distortion. So these are my top tips for how to answer loads and loads of questions that I've seen over the last 25 years of teaching physics. I've seen lots of exam papers, and the way that I've explained each of the specification references is trying to keep it as simple as I can, and you tell the examiners what I've said, and you should be able to pick up a lot of marks. So best of luck with your exams, and good luck for your future. Work hard, be nice, and bye for now.